Alright, my geometry geniuses, back with 9.6 video. This one's going to be another pretty simple section, I believe. Should be. It's just applying probability to geometric areas and stuff. So it's going to be taking, like the area of a small square within a big square. So taking that area of a small square out of the area of the big square. So we'll talk more about that. So above this on your sheet, and here's the colors. Make sure to label these because that's what goes along with these prompts here. So the bottom here is green. Doesn't show up green on your packet. On the left is red. On the right is blue, and on the top is yellow. So make sure you got those down. But above this, it says P equals the number of outcomes in the event over the number of outcomes in the sample space. So what we can think of when we think of that is, I'll write it out over here. So P equals number of outcomes in event over number of outcomes in the sample space. And so what we can think of this in terms that we've probably thought about it before. Sorry, let me point this up a little bit. Oh, there we go. So P equals the number of outcomes in the event over the number of outcomes in the sample space. So what we can think of this as is what we want to happen over everything that could happen. So there's that. And so the way we can think of this is like if you enter a raffle, you have you might say, oh, I got a 1 in a million chance I win it. But you really would have a 1 in a million chance of winning if there were 1 million tickets sold or given out and you got one of them, right? Because if one of those tickets are going to get picked and there's 1 million of them out there and you have one, then you really do have 1 in a million chance of winning, right? And that's because we have one ticket. We want our one ticket to be pulled out of those 1 million tickets. So there could be 1 million tickets, 1 million different tickets that could be pulled, right? But we want that one. So that's what 1 in a million comes from, or, a 2 in 3 chance, things like that. So let's go over this example quick. We're going to use a spinner to find the probability of each event. So what these are saying is that this is basically the angle of this right here, right? And this is helpful because we know that this whole thing is a circle, and a circle has 360 degrees. So, since we know that the total is going to be 360, let's try and keep that number in mind for the number of outcomes in the sample space. So we're going to use a spinner to find the probability of the pointer landing on yellow. So if we were to give this a flick, and it spins, assuming it's completely random, and I don't adjust the power of my flick at all, it's completely random, there is a what % chance that we land on yellow? Well, we're going to take what we want to happen, so we want to land on yellow, right? And we could divide it by everything that could happen. So when I spin this spinner, it can only land on the circle, right? But it could land anywhere on the circle. And so let's think about how we can break a circle up. Well, we know that a circle has 360 degrees. These are all labeled in degrees. So we can split this up with degrees. So we can take what we want to happen, this 140, and put that over, what do we do, 360 minus 140? No, because we want the denominator to be everything that could happen, including what we want to happen. So we'll do 140 out of 360, and that'll get us to 14 over 36, which is 7 over 18. And we can just keep it there. So we're just reducing fractions down from this to this, and we can treat this as a probability, or we can turn this into a decimal, or we can turn this into a percentage. But I'm just going to keep it here. You can go as far as you want, but 7/18 is the correct number there. So the pointer landing on blue or red is the next task. So let's erase this line. So we want blue or red. So this chunk or this chunk of pizza, not pie because we don't like pie. These chunks of pizza are what we want to land on. And so if we could have blue or red, we want to include both of these because both of these are spots that we want. So the probability of the pointer landing on blue or red is going to be red plus blue over the total. So if you see this or here, that means that you can basically add the probabilities together. So if I'm rolling a dice and I'm saying, what's the probability of it landing on 1 or 2? You have two options there. And so you can take the probability of both and combine them. So that's what we're going to do. We're going to take the probability of both. Since we have two options, we're going to combine them. We end up with 112 over 360, which ends up being 14 over 45. And lastly, the pointer not landing on green. So we're going to look at red, yellow, or blue, and not green. So there's a couple ways we could think about this. We could say, let's do 360 minus 108, because our possibilities are everything except for this green, right? So the whole 360 degrees besides these 108 degrees. So we'll do 360 minus 108 over 360, and that'll bring us to 252 over 360, which, believe it or not, is 7/10. So the probability of the pointer not landing on green, so landing on anything else, is going to be 7/10. And the other way we could do this is by finding what the probability of landing on green is, and then doing 1 minus that. So for example, that would be 108 over 360, which gets us to 3/7, and then 1 minus 3/7, or 3/10. 3/10, I'm so sorry. 1 minus 3/10 equals 7/10. So this is a probability of it landing on green. 1 minus that would be the probability of anything else. And you'll notice that they're the same. So like I said, this shouldn't be too difficult of a section for y'all. We'll get some practice problems in, but hopefully you can take the information from this module and we can get ripping in class. So thanks for tuning in, and we'll catch y'all soon.